So our last four modules were all about a t-test, and we're moving on now to a new kind of statistic called an ANOVA. This is an abbreviation that stands for Analysis of Variance, ANOVA. Before we start that, we need to review back from Module 2 what the concept of variance even is. So let's walk through the process again of calculating the standard deviation using the definitional formula. You see here the definitional formula is listed as the sum of all of the deviation scores squared. Remember, a deviation score is how far is a score away from the mean. You square each one to get rid of the negatives and sum them up. So if we have this list of scores here, we would, in order to find the mean, we would first sum them up, which would equal 30, and then we would divide by how many there are. That's 5, so the average is 6. Then the next step is to compute deviation scores. Each deviation score is the distance between the score itself and the mean. So 1 minus 6, negative 5. 9 minus 6, 3. 5 minus 6, negative 1. 8 minus 6, 2. 7 minus 6, 1. After that, we have to square each deviation score. So we take the squared deviation score, which is negative 5 squared, 25. 3 squared, 9. Negative 1 squared, 1. 2 squared, 4. 1 squared, 1. And then, in order to get the sum of those, the sum of the squared deviations, we add up the squared deviations. That comes to 40. Now, before we move on, what's this called? What do we refer to this number as? This is the sum of squares. After we finish computing the sum of squares, if you look up here, let's assume this is a population of scores. So we want to find next the variance of the population of scores. That equals the sum of squares over n. So you'd take the sum of squares here that we just computed and divide by how many scores there were. There's 5 there, so 40 divided by 5 is 8. Then, in order to finish this formula, remember when we drew an analogy back in Module 2 that was if you want to thread a needle, you blow up the needle really huge, you can shove your whole arm through. You can just grab a fistful of thread and put your arm through, and then when you're finished with that magic trick, you got to shrink the needle back down so that you can use it in sewing your button on or sewing your clothes or whatever. So here, in order to reverse what we did here, this is the standard deviation in squared form. This right here is the standard deviation in squared form. And before we move on again, I'll ask, what's this called? The variance. And what is the variance? It's the mean of the squared deviations, the average of the squared deviations, the average of them. Okay, but it's still in squared form. So in order to reverse that, in order to get it back down to its original form, in its original units, we take the square root of the variance. So the square root of 8 equals 2.83. That said, when we're computing a sample standard deviation, we have to change this value here. This, when we're computing a population, is the n. All the scores that exist. But when we're computing a sample, we have to use what's called the degrees of freedom, which is n minus 1. So if we were computing a sample variance and a sample standard deviation, the sample variance here would be 40 divided by n minus 1. So we have here 5 scores minus 1 is 4. 40 divided by 4 is 10. So then if we wanted to compute the standard deviation for this sample, we would take the square root of this 10, and instead of being the square root of 8 like it was before, the square root of 10 is 3.16. So remember, as you've completed your homework many times now, SS over DF is variance. Sum of squares divided by the degrees of freedom is variance. And we, in this chapter, are computing what's called an analysis of variance. So this principle of dividing SS over DF is going to come in a lot within this chapter, within this module. So here's an introduction to the analysis of variance, the ANOVA. The analysis of variance is used to evaluate mean differences between two or more treatments. It uses sample data as a basis for drawing general conclusions about populations. So you can imagine here that we have a population with an unknown mean, from which we draw a sample, and we give it treatment 1. We compute its mean, and we want to ask the question, is this population of all the people who've ever received this treatment or ever could receive this treatment different from population 2 who received treatment 2? We don't know their actual mean, but we do draw a sample from them and we compute the sample mean. And population 3 with a different treatment, treatment number 3, and we don't know their mean, but we draw from them a sample and compute their mean. We have to ask the question, is treatment 1 different from treatment 2? And is that different from treatment 3? Are there any differences in these means? So an ANOVA works like an independent measures t-test, where we have, remember in an independent measures t-test, we would have two populations and we would just compare the sample means for the two populations. But this has a clear advantage over the t-test. It can be used to compare more than two treatments at the same time. So if we have 3 populations, 3 different treatments, we can compare all of them and answer the question, are there any differences anywhere here? But before we move on, we need to establish a little bit of terminology. There's a phrase that's used when we're doing ANOVAs that's called a factor. A factor is the independent variable that designates the groups being compared. This could be a true independent variable or a quasi-independent variable. So a factor is the independent variable. Sometimes there's more than one, but there's always at least one. So if you have gender as your factor, then there are at least 2 groups, male and female. You might also have a third that's like non-binary. And when you have, like what we're talking about there is the, again, is a factor. But that factor has different levels. The levels are the individual conditions or values that make up a factor. So in the case of gender, like I just said, it could have at least 2 levels, male and female, but it might also have a third, non-binary, or you might have some other designations there. A factorial design is a study design that combines 2 or more factors. So if we add this IAL at the end of the word, then that means we've used more than one factor, more than one independent variable. Let me show you an example. This is what the structure of an independent samples or between subjects t-test looks like. You might have 2 conditions, no music and rap music. You would measure people's test scores after listening to no music while they study, or measure their test scores after listening to rap music while they study. And you'd have some 30 people in one group and maybe 29 or so in another group. A single factor ANOVA would add a third condition. So you might have some people listen to classical music in addition to your other 2 levels. You would then measure the test scores of those people who listen to classical music, and you would compare the 3 groups to each other to see if there are any differences anywhere among the 3 groups. But this is a single factor because there's only one independent variable, and that's music type. And the levels of that factor are no music, rap music, and classical music. let's work through this example. Here we have a therapy technique. We might have a first group and a second group that have two different kinds of therapy. One might be, I don't know, behavioral therapy, and another one might be like cognitive behavioral therapy. Then we have a time series as a second factor. And here we would say we've got before therapy, after therapy, and 6 months after therapy. And in each one of these cells, you would have some scores on some dependent variable that you're interested in. There would be scores for this group 1 that's measured before therapy, and scores for this group 2 that's measured before therapy. And group 1 measured after therapy, group 1 measured 6 months after therapy, and so on. So my question for you is this. How many factors would there be in a situation like this, where you've got 2 different types of therapy, and you've measured them at 3 time points? Hopefully you said there were 2 factors. This is the first factor. This is the second factor. My next question is, how many levels in each factor? Hopefully you notice that there are 2 levels in the first factor and 3 levels in the second factor. So let me ask this question. Is this a factorial design? You should say yes, because remember, if we use multiple factors, right here we have 1, 2 factors. If we use multiple factors, then we add this IAL at the end and we refer to it as a factorial design, meaning more than one independent variable, more than one factor. Are there any independent measures here? Remember back to our t-test modules when we learned about what independent measures were. They're groups that are separate from each other, not the same people. Are there any independent measures or independent factors? What about any repeated measures or any repeated factors? Hopefully you noticed that therapy technique was an independent measure. These are separate groups of people receiving 2 different kinds of therapy. But time is a repeated measure because we have the same group of people before therapy as after therapy and then 6 months follow-up. So here we've got a repeated measure. We're tracking them over time. Group 1 versus group 2. Those are independent measures. Now, in this module, we're only going to be evaluating single factor ANOVAs with independent measures. So we're not going to deal with these kinds of really complex designs here with multiple factors. We're not doing anything factorial in this module, and we're not going to do anything repeated in this module. We're just going to use independent measures on a single factor ANOVA. In future modules, we are going to cover concepts surrounding repeated measures ANOVAs and factorial ANOVAs, so that's the reason why I wanted to introduce this idea here now. But for now, we're just going to stick to our single factor ANOVAs where we just have one independent variable, and it might have 3 levels, which means 3 conditions, or 4 levels, like that, 4 conditions. Or it could have 5 or 6. It could have as many levels as we want, but they all have to be along one dimension, like music type or therapy type or gender or something like that. Okay, so when you're running an ANOVA, you have to write out your statistical hypotheses, just like we've been doing for the last several modules. The null hypothesis is that the level or value on the factor does not affect the dependent variable. So whichever condition or level you're in doesn't have any impact on the dependent variable. So in the population, this is equivalent to saying that the means of the groups do not differ from each other. So if you had treatment 1 and treatment 2 and treatment 3, their means, the means of those populations would be equal to each other. So all 3 means of all 3 different populations are the same if the null hypothesis is true and the treatments don't work. But the alternative hypothesis can't be written in a statistical notation with these symbols like we've been doing, because there are too many ways in which the null hypothesis can be violated. Look down here. Under what circumstances can the null be wrong? Well, it could be if all the means are different from every other mean, or it could be if some of the means are not different from some of the others, but other means do differ from some means. And so instead of writing this out in some kind of statistical format, we have to write in words something like, there is at least one mean difference among the populations. So we would violate the null hypothesis if mean 1 and mean 2 were the same, but mean 3 were different. Or if mean 1 and mean 2 were different, but mean 3 was the same as mean 1. Something like that. The test statistic for an ANOVA follows this format down here. But in order to make sense of that, I want to remind you first that the overall structure of a t-test that we've been doing for the last several modules looked like this. We took the obtained difference between two sample means. That might be, like, remember the independent samples t-test was when we took two sample means. Other t-tests were if we took like the same sample and repeated it, or if we took one sample and compared it to the population. But the point here is that we had a difference that we obtained in actual units. So one sample might be a mean of 5, and another sample might be a mean of 10. And the difference between those two, between 5 and 10, is 5 units. That's the obtained difference. And we divided that by the standard error, which was defined as the difference that we would expect between any two sample means at random if there was no treatment effect, if the null hypothesis were true. And so we would take that difference we obtained, like let's say it was 5, like we just talked about, and we would divide it by how big a difference we would expect there to be just by chance. And if that was a small difference, like 1, then we would say, whoa, that's a really big t. 5 divided by 1 is really big. But if the difference that we would expect just by chance is very large, like 10, then we would say 5 divided by 10 is only a half, 0.5, and that's a very small t that would fall right in the middle of the distribution. And so what we're doing here when we compute the t, if you recall, is comparing the size of the difference that we saw divided by the size of the difference we would expect to see if the null hypothesis were true and the treatment didn't work, just by chance. Okay. So an F ratio is actually very similar to that. It's just based on variance instead of sample mean differences. But we still take the differences, or the variance. Remember, variance is the differences, the size of the differences that we see in scores. So we take the variance or the differences that are between sample means, and we divide it by, or compare it to, the variance that we would expect if there were no treatment effect, if the null hypothesis were true, if the treatment didn't work. So the differences that we would expect to find just by chance. So we compare how big a difference we saw versus how big a difference we would expect to find just by chance if the null hypothesis were true and the treatment didn't really work. So this fraction that we were computing here for our F statistic, sorry, I forgot to say, an F is an abbreviation for ANOVA. You could call it an F test just as well as you could call it an ANOVA. Anyway, this fraction that we compute for our F is the same idea as the fraction we computed for our T. So we're just doing the same thing here that we've been doing for a long time. Now, one might wonder why we compare the variances in the F fraction, or the F ratio, instead of sample mean differences, like we did with the t-test. Well, the answer is that it's not possible to compute a sample mean difference between more than two samples. So for example, you might say, how much difference is there between 10 and 15? Well, it's easy, right? It's 5 points. That's a 5-point difference. But if you ask the question instead between 3 conditions, how much difference is there between 10 and 15 and 21? Ooh, that's not a possible question to answer. You can answer the difference between 10 and 15, or 10 and 21, or 15 and 21, but you can't answer as one question, what's the difference between 10 and 15 and 21? And so, instead of using the mean difference like we did in the t-test, just comparing two conditions, we have to compare the variance or the variability across these three conditions when we run an ANOVA. So let's talk about this, the test statistic that is an ANOVA. This F ratio is based on variance instead of the sample mean difference. The variance that's used to define and measure the size of the differences among the sample means is the numerator. And why do we use variance? Well, I've just described in the last slide that we have to use something other than the sample mean difference. So why do we choose variance? Because if you look at set 1 right here, you've got 3 different means. Let's say that these are treatment 1, treatment 2, treatment 3, and we've computed the mean for those 3 groups. Those 3 means are quite different from each other, 20 and 30 and 35. And if you compute the variance, S squared variance, for those 3 groups, you would get 58.33. Set 2 has 3 other imaginary treatments, 1, 2, and 3, but their means are much closer together, 28, 30, and 31. You can see how close they are together. The variance of those 3 means is much smaller, 2.33. So notice that the sample means in set 1 are far apart, right here, and their variance reflects that. See how large this variance is? So variance is a good measure of the size of the distance between sample means. So since we can't answer the question, what's the difference between 20 and 30 and 35, we can say instead, what size is the variance between these sample means? And here we have a large number to reflect large differences. And we could say, what's the variance between these sample means? And you have a small number to reflect small differences. Variance in the denominator of the fraction, underneath at the bottom of the F ratio, measures the mean differences that would be expected if there is no treatment effect, the size that you would expect just by chance. So going back up here, remember the variance in the numerator is defined as the measure of the size of the differences among the sample means. So we see the size of the difference that we do observe, and we divide it by how much we would expect to find if there was no treatment effect just by chance. Sometimes students wonder why we don't just repeat multiple t-tests. If we can compare population 1 versus population 2 and population 1 versus population 3 like this comparison, and then population 1 versus population 3 like this, why don't we just run 3 different t-tests in order to compare these differences and see which ones are different from each other? Well, the answer lies in type 1 error rates and how it's related to multiple hypothesis tests. Experiments often require multiple hypothesis tests, each one with a type 1 error. This is called testwise alpha. Now, when you run the first t-test of those 3 that we just talked about on the last slide, that has an alpha of whatever you've chosen. Let's say it's 0.05, because that's conventional. If the alpha size is 0.05 for each of those tests, and you run 3 of them, your alpha would be 0.05 for the first one, 0.05 for the second one, and 0.05 for the third one. You would have to add those together for an alpha of 0.15. And remember that each one of these represents the probability that you've made a type 1 error to say, there's an effect, this treatment worked, when really it didn't. This represents a huge increase in the probability of making a type 1 error. So instead of being wrong every 5 out of 100, you'd be wrong every 15 out of 100, or 15% of the time. ANOVA allows us to evaluate all the mean differences simultaneously with just one test, regardless of the number of means. Even if there was 10 different populations we were comparing, we could compare all 10 populations to each other and see if there are any differences among any of those populations. And thereby we would avoid the problem of inflated experiment-wise alpha, because the ANOVA has one alpha level. If we choose it at 0.05 and we run the one ANOVA test, then the probability of making an error on that one test is just the alpha, 0.05, whatever we set our alpha at. So this isn't associated with this same problem of multiple t-tests adding together the alpha level of each one and causing an inflation in our error rates. Now, I've kind of hinted at this a couple of times, but we might answer the question, why is it called analysis of variance? Notice that these scores are all different. Here we have a first treatment that is some people who don't use a phone, a second treatment that has a handheld phone, and a third treatment that has a hands-free phone while driving a car. And these people are in a driving simulator, and we want to know how many, how well their performance is. So let's say that high scores mean good performance. We would see that the average of these people who don't use a phone is about 4, high performance, compared to people who have a handheld phone or a hands-free phone, which both have a mean score of driving performance at 1. But these scores are all different. Somebody got a 4 here, somebody got a 3. Another person was in this driving simulator and got a 1. Another person over here was in the same driving simulator but used a hands-free phone and they got a 0. And this person got a 0 and a 1. They're all different from each other. In other words, they vary. Our goal is to measure the amount of variability, how much they differ. First, we measure the total amount of variance or variability, the total amount of differences between all of these different scores. Then we separate it into smaller parts. Hence, we're analyzing the variance. Hence, analysis of variance, ANOVA. We're analyzing the differences, the variability, the variance of all these scores. Now, there's multiple sources of variability here at play. There are especially, in particular, 2 main sources of variance, or of differences in the scores. The first one is between treatments, and the second one is within treatments. Between treatments refers to the differences between Group 1 and Group 2, between Group 1 and Group 3, between Group 2 and Group 3. Between treatments. There are 2 sources of variance when we analyze between treatments. Systematic differences caused by the treatments themselves, and random unsystematic differences that are just due to measurement error and individual differences. So let's look at that. The first one, systematic differences caused by the treatments. Some of these scores are much better than some of these scores. Not all of them, mind you, because, look, one person here got a 3, one person here got a 3. But on average, these scores are higher than these scores and these scores. There are systematic differences that are caused by the treatments. The difference between 4 and 0, or 4 and 1, or 4 and 3 is in part due to the fact that this guy here, we'll call him Joe, Joe has more experience driving than, say, Susan, who's here, or maybe Sally. But part of the reason also is because he is not using a phone. The systematic differences are the parts that are caused by the fact that he's not using a phone. But the random differences that are unsystematic are due to the fact that Joe has some experience driving that Jill or Sue don't have. But some of the people here in this group will have less experience driving than some of the people here in this group. Some of them will have woken up on the wrong side of the bed. Some of them won't have had breakfast, and some will. Some will have arrived late at the driving simulation experiment, and some will have Some will just be a little shorter than others, and they won't be able to reach the petals as well. And there's just all kinds of random differences between all of these different scores. And those random unsystematic differences contribute to the differences here that we see. But we also see that some of the differences are due to these systematic differences that are caused by some people not using a phone, some people using a handheld phone, and some people using a hands-free phone. There are no systematic differences within each group. At least if you've designed your experiment well, you hope there aren't any. So there's only one source of variance within treatments. That is, if we take one of these treatments and look within it, inside of it, within the treatment, there are differences. 4 is not the same as 3. Joe is not the same as Bob, and Bob is not the same as Suzette, and Suzette is not the same as I don't know. Anyway, these people are not the same as each other. These differences are not due to any treatment effect, though. They're just due to random, unsystematic differences that are because of measurement error and individual differences. Okay, we have to demonstrate that any observed differences that we see in the groups are greater than what would be expected by measurement error alone. So, any differences that we see here between 4 and 1 and 1, we have to demonstrate that that difference of 3 points here and of 3 points here and of 0 points here, that those differences are greater than what we would expect just because of random differences across groups within each group, the random differences across individuals within each group. In order to do that, we take the total variability and we split it into these two parts, the between treatments variance and the within treatments variance. Just like we talked about on the last slide, between treatments variance are those differences that are between the conditions, the difference between 4 and 1 and 1. But those differences can be chalked up to two sources of variability. One is the systematic differences because of treatments, like which kind of phone do you use, and the other source is because of random individual differences and unsystematic factors. When you look at the within subjects treatments, within each condition, within each group, you look at the source of variability inside that group and see that there are only differences because of random unsystematic factors. If we compare these two things against each other, the differences including any treatment effects, the differences both because of randomness and because of systematic treatments that include any treatment effects, and we divide it by the differences with no treatment effects, right here, the differences that we just find randomly by chance without a treatment effect, then we get our F statistic. Another way of saying that would be to say we could take the F being equal to between treatments variance here and dividing it over within treatments variance here. You could also say instead that the F statistic is the systematic treatment effects plus random unsystematic differences. And we divide that by the random unsystematic differences. So it's both of these combined divided by just the one alone. However you think about it, what we're doing here is we're saying that we're trying to take the systematic treatment effects, the size of the differences because of the treatment, and the size of the differences because of just random individual differences, and divide it by how much difference we would expect there to be just by chance because of randomness. Let's take that definition of the ANOVA, the F ratio, and talk about the numerator and the denominator. The denominator of the F ratio is called the error term. This denominator is called the error term because it's an estimate of the error variance, or the variance that's just due to random stuff. Remember, in statistics, the word error is the stuff that we haven't accounted for. It's not a mistake that we've made. It's just stuff that we haven't accounted for. In this case, it would be the differences between individuals just because of having woken up at different times in the morning and arrived at different times at the shop, and some people being more frazzled, and some people being taller, and some people being shorter, and some people eating breakfast, and some people not, and some people have more driving experience, and whatever. All those individual differences we chalk it up to error. It's stuff that we haven't measured. So in the bottom, we call that error. In the top, we call this the treatment effect plus the error. If the null hypothesis is true, then the size of the treatment effect is near zero because the treatment didn't work. There is no difference because of the treatment. The treatment is nada, null, nothing. There is no treatment effect if the null is true. If that were the case, then we would have an approximate estimation of the degree of error divided by the degree of error, because the treatment effect would be nothing. Error over error is near 1, because let's imagine what error values we could have here. If the degree of error in this experiment were 3, and we put it here and we divide it by 3, 3 over 3 is 1. If it was 10 over 10, it'd be 1. 8 over 8, 1. Whatever it is, whatever the degree of error is, over itself, it should be about 1. Now, it's not always going to be exactly 1 because error is error. It's going to be variable. It's going to just be slightly different. So the differences that we see between our groups are just going to have like a little bit different of differences than the differences that we see within each group. And so it's not really ever going to be exactly 1, but it's going to be something close to 1 if the null hypothesis is true. But if the alternative hypothesis is true, then the size of the treatment effect is more than 0. It's some value here. And if we take this value and we add it to the error and we divide by the error, then this should be noticeably larger than 1. So let's say the error was 3. We plug in 3 here for the error and 3 here for the error, but our treatment effect was a size of like 10. That would be 13 divided by 3, something much larger than 1. Before we move on, we need to talk about some ANOVA notation. Here in this table, we have the same scores that I showed you before. These are the no phone group, the handheld phone group, and the hands-free phone group. But we have here a bunch of letters underneath and a bunch of computed values and some off to the side here. Because ANOVA involves a lot of calculations, I'm going to explain to you what these letters represent. First, the little n in this situation means the number of scores in each treatment. Like N1 or N2, you put a little sub next to the treatment number. So this is treatment 1, so all of these have here a sub 1. This is treatment 2, so they all have a sub 2. But N is the number of scores inside this treatment. So here there's 5 scores. Little n equals 5. K represents the number of treatment conditions. You can see here we have treatment 1, treatment 2, treatment 3, so K is 3. The total number of scores is a capital N. I know in a previous module that we talked about capital N representing the number of scores in a population, but here in this module we're going to change the definition of capital N. Capital N in the scientific literature doesn't always mean the number of a population anyway. Oftentimes when you see a published paper, they'll use a capital N to represent their sample size in that paper. There's not a uniform convention for the letters that we use in statistics. Not all the time. So in ANOVA, in this chapter, or in this module, I'm going to use capital N to represent the number of scores in the whole experiment. That is 5 plus 5 plus 5. So you might have noticed that if all the samples are the same size, like they're all 5 here, then the big N is equal to the little n times the number of conditions. So 5 times 3. But if they're not the same, then you can just add up how many there are in each condition, and that's the total n size. T represents the sum of the scores for each treatment. So the sum of X for each treatment. If you add up 4 plus 3 plus 6 plus 3 plus 4, that comes to 20. If you add up 0 and 1 and 3 and 1 and 0, that comes to 5. So the T for each condition is the total sum of the scores for that condition. G represents the grand total of all the scores in the study. So if you take the sum of your individual T's right here, then that will add up to your grand total. But you can also just take 4 plus 3 plus 6 plus 3 plus 4 plus 0 plus 1 plus 3 plus 1 plus 0 plus whatever these are. Final note here. There is no universal notation for ANOVA, just like there's no universal notation for most of what we do in statistics. These are the letters that we're going to use in this class, but other sources might use other symbols. So don't memorize these and think that they're always going to be universally used in every class that you might take on statistics. This is just what we're going to use for convention here in this course. Now, let's do a self-check. I'm going to ask you, how do you get each one of these kinds of things? And I want you to compute it. So pause your video after I ask you one of these questions, and then we'll answer it together, and you can test your knowledge. So first, how do I get T? T is the total for each condition. So you would add up these scores for the first, these scores for the second, and these scores for the third. How do I get the sum of squares? Remember, the sum of squares is the sum of the squared deviations from the mean. So you'd take the mean of this group right here, and you would subtract from it you'd subtract from each score the mean of the set of scores. You'd square that deviation, and then you'd add them all up. That would be how you get the sum of squares. How do I get little n? Little n is the number in each condition. So n1 is 5, n2 is 5, n3 is 5. How do I get m? Remember, this italicized m represents the mean. Hopefully you remember that you add up all the scores and divide by how many there are. How do I get the sum of x squared? That would be to take each of these scores and square it, and then sum them all up. So in this case, you get 106, because if you took 4 and squared it, and 3 and squared it, and all those, and squared these, and added up the sum of all of those, you'd get 106. How do I get G? Remember, G is the grand total of all the scores, so you just add up these, and these, and these, or you can add up these, and these, and these, because the sum of the T's is also equal to the G. How do I get capital N? Hopefully remember that this is the number of scores in the entire study. So capital N here is 15. And how do I get K? It's the number of conditions in your study. So there's 3 conditions, which means there's 3 Ks. All right. An ANOVA calculation follows a series of 9 steps. The first one is to figure out the sum of squares total, then the sum of squares between, and the sum of squares within. Just like I explained before, you take the variability and you split it into 2 parts. Here, step 4, you figure out the degrees of freedom total, and then you split it into 2 parts, the degrees of freedom between and the degrees of freedom within. After you finish those first 6 steps, then you compute the variance between treatments, which is the sum of squares between divided by the degrees of freedom between. Remember, variance is SS over DF. So we're computing the variance between by restricting ourselves to the variance, the sum of squares between, and the degrees of freedom between, and putting those in a fraction. Step 8 is to take the variance within treatments, SS over DF for within. So you take this SS within and this degrees of freedom within, and you pit them against each other, and you get this variance within. And then finally, your step 9 is to take the variance between treatments and divide it, like we said before, by the variance within treatments, which represents the variability you see because of the treatments and error, divided by the variability you expect just by chance because of error alone. So, step 1, we have to partition the sum of squares for independent measures ANOVA. First, we compute the total sum of squares. The formula for that is the sum of x squared minus g squared over n. You might say this looks familiar. It should, because it's basically the sum of squares formula that we've been using all along, with g replacing the sum of x here. Then you take the sum of squares total and partition it into two parts: the sum of squares between treatments and the sum of squares within treatments. A formula is given here for the sum of squares between treatments. Students often get confused here, so I beg you, please pay attention to this. The sum of t squared over n represents the t for each condition squared divided by the n for that condition that you took the t. After you figure out that for each condition, then you sum them up and then subtract this component of the equation. So if you have 3 conditions, then you'll have this part here plus another part here plus a third part here, and sum them up and then finally subtract g squared over n. The sum of squares within treatments is the sum of squares that you find inside each treatment added up. So if the sum of squares for the first treatment and the sum of squares for the second treatment and the sum of squares for the third treatment were added together, then you would get the sum of squares within. So let's work through an example. Here we've got our same condition that we talked about before, our same experiment, where we have no phone, a handheld phone, and a hands-free phone. In order to compute the sum of squared total, we follow this formula. That's the sum of x squared minus g squared over big N. If we plug in these values, the sum of x squared is 106. We put that right here. For g, we find 30, and we put it right here. And for big N, we have that here, and we put it there. So 106 minus 30 squared over 15, and that equals 46. The sum of squares within treatments is adding up the sum of squares for each of the inside treatments. So if you take the sum of squares here, and the sum of squares here, and the sum of squares here, and add them together, that's the sum of squares within. The sum of squares between is the sum of all of these components for each condition minus g squared over n. So the t squared over n, remember, is the first t squared divided by n, and then the second t squared divided by n, and the third t squared divided by n, and then you sum those up. So 20 squared over 5, 5 squared over 5, 5 squared over 5, add those up, and then finally subtract g squared over n, which is g here, 30 squared divided by 15, that n right there. So if you carry that through, you've got 80 plus 5 plus 5 minus 60, that equals 30. Notice that the sum of squares within and the sum of squares between add up to the sum of squares total. 16 plus 30 is 46. That will always be the case because when you figure out the sum of squares total, what you're doing is dividing it into two kinds of variability. The sum of squares that's within each treatment and the sum of squares that's between all the treatments. Alright, the next thing that we need to do is partition the degrees of freedom. You take the degrees of freedom total by computing big N minus 1. The degrees of freedom between treatments are k minus 1, the number of conditions minus 1. And the degrees of freedom within treatments is the sum of the n for each group minus 1. You can also compute big N minus k, and it gives you the same thing. But to me it makes better sense to do the sum of the n for each group minus 1 in each of those cases. I'll show you both in the next slide. So degrees of freedom total equals big N minus 1. That's big N 15 minus 1 is 14. Degrees of freedom total is 14. The degrees of freedom within, by one computation, is big N minus k. 15 minus 3 is 12. By another computation, it would be little n minus 1 for each condition added up. So 5 minus 1 is 4, 5 minus 1 is 4, 5 minus 1 is 4, and add the 4 plus 4 plus 4 is also 12. The degrees of freedom between is computed as k minus 1, the number of conditions minus 1. So 3 minus 1 is 2. Notice here again that the degrees of freedom within and between add up to the degrees of freedom total. 12 plus 2 is 14. And that's because when we take the degrees of freedom total, we're splitting it into two different sources of variability, within and between. Woo! It's party time! We finished steps 1 through 6! Booyah! You thought that was going to be much harder, didn't you? Yeah, well, it's not that hard. Here we finished 1, 2, 3, 4, 5, 6. All we have left is 7, 8, and 9. So the next step is to compute the variance between treatments and the variance within treatments. Remember, as I said before, variance is SS over DF. You've written that in your homework so many times now, you couldn't possibly be confused by that, right? Variance is the sum of squares over the degrees of freedom. It's a fraction that represents the amount of variability still in its squared form. In ANOVA, it's customary to use the term mean square, however, instead of variance, or we abbreviate it simply MS, in place of the term variance. Why? Because, as I said at the very beginning of this presentation today, variance is the mean of the squared deviations. It's the average squared deviation. It's the average amount of variability still in its squared form. So just like SS stands for sum of squared deviations, MS stands for the mean of squared deviations. So I know that I've drilled and drilled and drilled and hammered and hammered and hammered into you that SS over DF is variance, but now I'm going to tell you SS over DF is mean squares. It's the same thing. Mean squares means variance. It's the same thing. We're just going to call variance mean squares instead of variance for the length of this module. So remember that variance, or mean squares, is calculated as SS over DF. Therefore, if we want to figure out the mean squares between, or the variance between, then we take SS over DF for the betweens. And if we want to compute the mean squares within, or the variance within, then we take SS over DF for the withins. I've listed up here all the things we previously computed in our first 6 steps. So you should be able to take SS between 30 and divide it by the degrees of freedom between 2 and yield a mean squares between, or variance between, of 15. In order to get the MS within, you should take the sum of squares within, 16, and divide it by the degrees of freedom within, 12. You should find that that mean squares within, or variance within, is 1.33. Okay, now we've finished steps 7 and 8. We finished the SS over DF between and SS over DF within, so we know our variance fraction, and all we have to do is pit them against each other now in step 9. So to compute the F, the final step, we take the variance between, or as we're calling it now, the mean squares between, and we divide it by the variance within, or the mean squares within. We just computed both of those on a previous slide, and we pit them against each other by putting 15 over 1.33, and we get an F ratio of 11.28. Our F, our ANOVA, is 11.28. When you use a computer to calculate your statistics, you'll see your results placed in an ANOVA summary table like this. I recommend you start with a blank summary table and fill in the values as you compute them. This will keep you on track to help you avoid getting lost. So notice that we have the word source here to represent the type of variability that's between treatments and within treatments versus total. And you can say, you can compute the SS and the DF and the mean squares. And you remember we did this as step 1, I think it was 1, 2, and 3, or 1, 2, and 3, it doesn't matter, but this is the first 3 steps, second 3 steps, steps 7 and 8, and step 9. If you write out your table like this, then you will know that you need to fill out these 9 pieces of information in that order like that. Now, I haven't explained to you how we use an ANOVA in a hypothesis test, or how we interpret the ANOVA when it's finished. But before we go on, I really strongly want you to pause the video and practice going through a scenario, computing the ANOVA, all 9 steps. Use your formula sheet, where I've listed out the formulas for all your sum of squares and all your degrees of freedom and your variability, your mean squares, and your F ratio, and you should be able to use this information. I haven't given you the scores because you don't need them here when I've given you all this information so far. Okay, if you have all this information, you don't need the scores. But you should be able to figure out, based on this information, for treatment 1, treatment 2, and treatment 3, your F ratio. That's your goal. So pause the video and figure out your ANOVA, your F ratio, using those 9 steps. Okay, hopefully you found that these were your answers. If you used your ANOVA summary table, it will have kept you on track. Check your answers there and move on when you're ready. Now, the distribution of F ratios takes a particular form. It's a form that's unlike the T statistic distribution or the Z statistic distribution. That was a normal curve. Instead, if the null hypothesis is true in the ANOVA situation, then the value of your F statistic will be around 1. Remember, I demonstrated that before, because you've got no treatment plus error divided by error, so it should be something near 1. Because F ratios are computed from 2 variances, they're always going to be positive numbers. Remember, variances are variability differences in their squared form, and squared numbers are never negative. So it's one positive number divided by one positive number, so it's always going to be a positive number. It's still, we're comparing values in their squared form. So given these 2 facts, the F distribution of scores has to look like this. It never goes below 0, and it usually, if the null hypothesis were true, should be centered around 1. Most of the scores, if the null hypothesis were true, just by chance, would be about 1. Now, this is a null distribution, so every once in a while, just by bad luck, just by chance, you're going to get F statistics that are much larger than 1. There's no good reason for it. It just might happen because of chance from time to time. But most of the time, you'll find F statistics in this part of the distribution because this is where most of the scores are. And rarely will you get, just by chance, an F statistic of something much higher than 1. The exact distribution, the exact shape, the exact height of this peak, and the exact number of scores out here in the tail will depend on the number of scores, or, in other words, the degrees of freedom. So the table of F values that you should have downloaded and perhaps even printed before you started this module is organized by 2 degrees of freedom. It's labeled in the table as numerator and denominator. I hope that you've printed it so that you can write in on the table between and within, because those are the words we're going to be using, and it's a little confusing to have the table labeled numerator and denominator. So just pencil in, write in, next to the numerator, between, and next to the denominator, within. So we're going to look up the critical F values that we should have gotten in this situation about the cell phone experiment in the table corresponding to the degrees of freedom that we had in our example, which were 2 and 12. So here's an example of what the table looks like. You've got degrees of freedom numerator and degrees of freedom denominator. But remember, we're labeling that between and within. So between, within. In order to find the correct critical F statistic for this example, we use between and within degrees of freedom that we computed before, 2 and 12. We come to our table and we figure out 2 and 12, where they intersect are these two values here. The value in normal face is the value if your critical alpha is 0.05, and the bold face value is the one that you would use if you had an alpha of 0.01. So we could use either 3.88 or 6.93, depending on how stringent of an alpha value we wanted to use. So if the null hypothesis were true, only 5% of all the possible scores from the null distribution would yield an F statistic above 3.88, right here, marked in your chart right here. And only 1% would yield an F statistic above 6.93, this second value, which is marked right here. So, if the null hypothesis were true, and the treatment really didn't do anything, and all the populations that you drew samples from were really the same, you would expect most of the time to find an F statistic that was around 1. Might be a little higher because of the particular degrees of freedom we have here, but you would expect it to be somewhere in this region. Every once in a while, just because of bad luck, just because of chance, you might find an F value that's much higher than this. But if you find an F value much higher than this, you assume it's not because of chance. Instead, you assume that means there really is a difference between some of your groups. And so we reject the null hypothesis, and we say, even though it's possible that we just got this F value really big by chance, more likely what we think is that the treatments worked, and there is some difference in the populations of these treated values. So let's walk through an example of hypothesis testing. Oh my goodness, we've done all the steps of an ANOVA, so let's put them together to perform a full-blown hypothesis test. In this research study, let's use the question, what method of studying best helps students learn material before taking a test? We'll have 4 conditions here. Some might read the material once, some might read the material twice, some are asked to answer questions that have already been written, and some students are asked to create their own questions and answer those. Here are 4 conditions. Read once, read and reread, answer prepared questions, create and answer questions. I have given you all of these values here for the sake of expediency, but you know how to get these. You know how to compute the total n and the big G and the sum of x squared and the t and the m and the ss. And you may be asked to do that on homework or on a test, so please be prepared. Don't forget what these represent, even though I'm giving them to you here. Step 1. State the hypotheses and select an alpha level. The null hypothesis is that the mean of the first group equals the mean of the second group equals the mean of the third group equals the mean of the fourth group. All the groups are the same because none of the treatments have any difference compared to each other in this situation where the null hypothesis is true. In the alternative hypothesis, we say, in words, at least one of the treatment means is different. In this situation, let's use an alpha of 0.01. For no particular reason, we're just doing that. Step 2, we have to locate the critical region. So in order to do that, we first have to find the degrees of freedom between and the degrees of freedom within, because those are needed in order to look in our table. So the degrees of freedom total in this situation is what? Remember, it's 24 minus 1, 23. And then we split that into 2 parts. the degrees of freedom between, and the degrees of freedom within. How do we compute the degrees of freedom between? Remember, it's the number of conditions minus 1. 4 conditions here, minus 1 is 3. The degrees of freedom within, remember this is the number of scores in each condition minus 1. And you add them all up. So you have here 6 scores minus 1 is 5. 6 scores minus 1 is 5. 6 scores minus 1. 6 scores minus 1. 5 and 5 and 5 and 5 is 20. That's the degrees of freedom. But this and this add up to that. Then we look in our table for our critical F. We use degrees of freedom between and degrees of freedom within here on the numerator and denominator. So we use 3 and 20, find the intersection here. And because we chose an alpha of 0.01, we use the bold-faced value, which is 4.94. That's the F value that we need to get an F value of higher than in order to conclude that our ANOVA, that there are differences between these groups. So we draft it out. It looks like this. It peaks around 1. We draw our critical region here at 4.94, and this is the top 1% of scores that we might find if the null hypothesis were true. Just by chance, they might be larger than 4.94, but most of the time, they're not. Most of the time, 99% of the time, they're going to be lower than 4.94. And so if we get one that's higher, it's possible 1% of the time it could just be a random error because of chance. But more likely than not, if we get one that's in this critical region, it's because there's a difference, a real difference between these groups. One of the treatments, at least one of the treatments, worked. Step 3 is to compute the F ratio. So remember we have an ANOVA summary table down here with SS, DF, and MS. We have to figure out steps 1 through 3, 4, 5, 6, 7, 8, and F. Well, we already figured out the degrees of freedom, remember? Because we had to do that in order to find the critical F value. So let's now figure out the sum of squares. Here are our formulas. The sum of the x squared minus g squared over n. That is 1298 right there. G squared, 168 squared, divided by the big N, 24, equals 122. The second one is the sum of squares within treatments, which in other words is the sum of squares that's inside each treatment. So the sum of squares here, plus this one here, plus this one here, plus this one here, 20, 20, 14, and 8 is 62. And the sum of squares between is this somewhat complicated formula where we have to take the t for each group and square it and put it over the n of that group and then sum all of those up. So we take this t, square it, divided by the n size in this group, which is 6. The t here squared divided by 6, t squared here divided by 6, t squared here divided by 6, and add all of those up. So 30 squared over 6, 36 squared over 6, 48 squared over 6, 54 squared over 6. And then finally we subtract g squared over n. This g is 168 squared over big N, 24, down here. If we carry all of this through, we get 60. So let's take those three values, put them in the table right here, and then finally we need to figure out our mean squares, our variance, our variability here, which is, of course, as you know, SS over DF. So we're figuring out that SS over DF for between and SS over DF within. So 60 over 3 is, as I showed you up here, the formulas. 60 over 3 is 20, and 62 over 20 is 3.1. So we put those in the table there. And the last step, step 9 of the ANOVA test, is to figure out 20 divided by 3.1. MS between over MS within, or variability between over variability within. And that equals 6.45. If you put that here in the table, then you've completed your entire ANOVA test. We have to now, as step 4, figure out what to do with this 6.45. If we look at our original distribution, we marked off the critical region as anything above 4.94. Our obtained value was here, which means we reject the null hypothesis and we say we obtained a value that we would not expect to get by chance if the null hypothesis were true. Therefore, we conclude that there is a significant treatment effect. In other words, there's at least one mean difference between those four groups. But we don't yet know which two means are different. All we know is that across those four conditions of reading once, reading twice, answering pre-written questions, and answering questions that you've written yourself, all we know is that there's a difference somewhere. But we still have to figure out where is the difference. In order to do that, we run what are called post hoc tests. Post hoc is Latin for after the fact. So after we've run our ANOVA, then we can run these after the fact tests, these post hoc tests. Remember, the ANOVA compares all the individual mean differences simultaneously in one test. So all the four groups' differences are compared at once, and we have one alpha level, but a significant F ratio indicates that at least one difference in the means is statistically significant, but it doesn't tell us which means differ significantly from each other, and so we run these post hoc tests to tell us which mean differences are significant and which ones are not. But note that you should only perform the post hoc tests if you rejected the null hypothesis. If you didn't, that means there are no differences, and there's no point asking where are the differences if there are no differences. So this test answers the question, where are the differences? Now before I show you how to calculate that, I want to show you why this, basically how this works and why it's okay. Our post hoc tests actually do the same thing as individual t-tests would do. It compares population 1 versus population 2, population 2 versus population 3, and population 1 versus population 3 in 3 different tests. I told you before that we should never do that because it influences our type 1 error rate. It inflates it a lot. In this situation, the risk of type 1 error accumulates and is called the experiment-wise alpha level. In other words, across your entire experiment running multiple tests, you've got the alpha of 0.05 plus the alpha of 0.05 plus the alpha of 0.05, and you end up with an inflated error rate of 15% of the time. So, increasing the number of hypothesis tests increase the total probability of making a type 1 error, but post hoc tests use special methods to try to control that experiment-wise type 1 error rate and keep it lower than it should be if we had just not made any kind of correction. So it would be about 15% error rate if we didn't make a correction, but the post hoc tests use special methods to correct for that. Tukey's honestly significant difference, abbreviated HSD, Tukey's HSD is one kind of post hoc. There are dozens upon dozens of post hoc tests that you can run that try to correct for that inflated error rate in different ways. But this is a relatively simple one, so we're going to use it. The Tukey's HSD provides for you a single value that determines the minimum difference between treatment means that's necessary in order to claim statistical significance. A difference that's large enough that the probability is less than the alpha experiment-wise. Let me say that in clearer terms. If you compute the HSD, it gives you a number, and you compare your mean difference for first group minus second group, first group minus third group, second group minus third group. You compare each of those differences against this value, whatever this is, and you see if your difference is bigger than this, then it's a real difference, and if it's not, then it's not a real difference. And then we've controlled for the alpha across the whole experiment by computing one value that's a critical value against which we can compare all of our other differences. Now, in order to compute this, the formula here has a Q. This Q is found in another table that I've asked you to download before you started this module, called table B.5. The sample size n here must be the same size in every sample of your experiment for this particular test to work. So if one of your groups had like 20 and another one had 22, then you couldn't use this HSD test. You'd have to use a different type of post hoc. But here, in this example, we have the same size groups for each of the 4 conditions. Remember, each one had 6 people in it, and so we could put this value down here as 6. But before we run that, we have to figure out what is our Q. The value for Q comes from this table B.5, like I mentioned, and in order to find it, you need 2 pieces of information. The first one is K, the number of treatments, and the second one is the degrees of freedom for the error term. You should remember that the degrees of freedom for the error term is DFW. You hopefully have printed this out and you can write a W up here or within in order to remind yourself that this degrees of freedom for the error term is DFW, degrees of freedom within. We have 4 conditions, 4 numbers of treatments. The first one was read the material once, the second one was read the material twice, the third one was answer questions somebody else prepared for you, and the fourth one was answer questions you wrote yourself. So we find the intersection between the number of treatments and DFW, which we computed as 20. So we follow this down here to DFW 20, 4 conditions, and these are the 2 values that we could possibly use as Q. But in order to decide which one, we have to use either the light face if our alpha is 0.05, or the bold face if our alpha is 0.01. In this situation, if you remember back, we used an alpha of 0.01, so we should use our Q value with the same alpha, and this right here is the Q that we put into that formula. So here is our HSD, Q is 5.02, mean squares within up here is 3.1, the n size of each condition was 6. You plug all those in, follow it through, and it equals 3.61. Now, what do we do with this? This is the standard against which we compare all of the mean differences. So if Tukey's HSD is 3.61, then which of these differences is significant? Group 1 minus group 2 is a mean difference of 5 minus 6, or a difference of 1. I'm not putting the negative values here because it doesn't matter whether we subtract the second minus the first or the first minus the second. I'm taking the absolute value because I just want to know how far apart the 2 means are, and they're 1 distance apart, 1 unit apart. The difference between A and C, which is 5 minus 8, that's a difference of 3. The difference between A and D, the first group and the fourth group, or 5 and 9, 5 minus 9, a difference of 4. And you could compare the rest, B minus C, B minus D, C minus D, and in each of those conditions, if you take the mean and compare them across, and you do all those mean comparisons, you need to see which of these mean differences is larger than 3.61. And you should notice that only one of these is larger than 3.61, so that is the only mean difference, 9 compared to 5, that's actually significantly different from each other. All the rest of these are not different from each other. They are technically, literally different, like none of them are exactly the same. 5, 6, 8, and 9, none of them are the same, but statistically, they are not significantly different from each other. We couldn't conclude that group 1 and group 2 are different from each other because they're too close together compared to how far apart you'd expect them to be just by chance. I want you to now remember that when we went through all of our previous t-test modules, that if we found a significant difference, that only meant it's unlikely to have occurred by chance. It didn't tell us whether it's an important or a big difference, and that's what effect sizes are for. In an ANOVA, we don't run the R-squared like we used to with the t-test, but we run something that's almost the same. It's really interpreted the same and it's computed very similarly. It's called eta. This is a Greek letter eta squared. So the eta squared computes the percentage of variance that's accounted for by the treatment conditions. Remember, that's the same as how we were interpreting r squared before, the percentage of variance that's accounted for by the independent variable, or by the treatments. So this is a lot like r squared, which was the proportion of variance explained by the treatment effect. It's just computed slightly differently. Here we take the SS between divided by the SS total. Remember that SS between includes all the differences, all the variability here that was between the treatments, between meaning because of the treatment effects. So this is the variability that's because of the treatment differences between the one condition and the others. If we take that treatment effect size and we divide it by all the total differences that we see across all the scores in the study, then this number divided by this number tells us that 0.492 is our eta squared. How would we interpret this? Hopefully you would remember that when interpreting an r squared, we would say 49% of the variability in people's test scores after they studied in these different ways can be attributed to the particular way in which they studied. We interpret the eta squared in the same way. So we'd say 49% of the variability in these students' test scores can be attributed to their treatment condition, or can be attributed to the type of study condition that they were placed in. All right, after we finish all of these steps, we have to write it up in the literature. In order to do that, we have to put the means and standard deviations for each of the conditions in a text, table, or graph. In most of the situations in this class, I'm going to expect you to put it in a table like this. And then in addition to that, you'll reference in your write-up that you can find the means and standard deviations in this table or in the graph that you've drawn or whatever. You also include the results of the ANOVA test with the F and degrees of freedom, and the p-value, and the eta squared. So here's an example. The means and standard deviations of each condition are presented in Table 1, so you've referenced the table. The analysis of variance indicates that there are significant differences among the 4 study strategies. Then you put a comma. You italicize your F, and you put inside the F the degrees of freedom between and the degrees of freedom within. You then put equals what the F value is, comma, p less than 0.01. Then you list your eta squared, 0.492, and you would say what your post hoc test showed if you ran them, if your ANOVA was significant. Tukey's HSD post hoc analysis revealed that creating and answering questions was better than reading only once, with a p less than 0.01. Before we wrap up this module, there's a couple of reminders I want to give you. These are things we've talked about lots of times throughout the course. But here I want to show you that if you had 2 very similar experiments, but the variability in the treatment types was large in one and small in another, you would draw very different conclusions from your ANOVAs. So here, treatment 1 and treatment 2 are quite, they're the same distance apart, 8 versus 12, as in experiment B, where treatments 1 and 2 are also 8 versus 12. But in the first experiment, you've got scores that are very close to each other in each of the 2 conditions. In experiment B, the scores are much more variable, much further apart. If you graph this visually, you'll see something that we've seen many times before. If you cluster all the scores together, that's these, and all the scores here, that's these, it's quite easy to see between treatments that there's a mean difference between 8 and 12. That 4-point difference becomes very obvious. Your statistic should find that there's a big difference between them as well. But the mean of your white scores and the mean of the teal scores down here is the same distance apart, but when you compare it to the amount of error variability it's very difficult for your statistic to determine whether this 4-point difference is meaningful or if it's more than you'd expect just by chance. So my question is, would you expect to find a significant F ratio in either one of these experiments? And why? Hopefully you would recognize that this would have a significant F, because this group and this group are obviously different. In fact, if you compute the F, it's 83.96. That's an enormous F, way bigger than 1. In experiment B, you've got an F statistic that's very close to 1, just what you would expect to find just by chance, because these scores are so spread out and overlapping that you can barely tell a difference between the two groups. The point here is to help you see that the numerator of the F statistic is the same in both situations, 56 and 56, because that represents the difference between 8 and 12 as the mean difference in these two conditions. The denominator measures the variance of scores inside each treatment. So here, there's very little variability inside of this treatment and very little variability inside this treatment. But here you can see there's a lot of variability inside the two treatments. The white ones are spread far apart and the teal ones are spread far apart. And so you find a lot more variability just by chance, that error variability. So it's bad to have a lot of noise within your conditions, because when you pit against each other the treatment difference and the random error differences, you will see that you'll get a very large score if the differences are far apart, and a very small score if the differences are not that far apart. There's another principle here I just want to drive home, and that is that if you only have two conditions in your factor, in your independent variable, you can run either a t-test or an f-test. And in fact, you'll always get the same decision if you use the same alpha, because f will always be equal to t squared. If you look in this example, we might use a two-tailed t that results in critical values of plus or minus 2.101. If you square that value, 2.101 squared is equal to the critical F statistic of 4.41, and that would be in this one tail, because an F value always has only one tail. There is no such thing as a negative F value. So for any value of alpha, the T critical squared is also going to be equal to the F critical. So whatever your computed statistic is and whatever your critical statistic is, they're always going to be closely related to each other in that the T squared is equal to the F. And the reason for this is because this is an analysis of variance, the standard deviation still in its squared form. The t-test is comparing the difference between two means in terms of standard deviations, which are no longer in the squared form. So the reason why this is squared compared to this is because here we're looking at differences in terms of standard deviations, and here we're looking at differences in terms of variance. This allows us to compute more than two mean differences. This doesn't. But if you have only two mean differences to compare, you can run either a t-test or an f-test, and it will get you the same answer. It will not be the same value. The f and the t won't be the same value, but the conclusion to reject the null hypothesis or to fail to reject the null hypothesis will be the same regardless of which type of test you use. There are some assumptions associated with the independent measures ANOVA. Those include the observations within each sample have to be independent. The number of scores in each condition should be equal, but they don't have to be. The population from which the samples are selected must be normal, but we sometimes violate this assumption if the sample sizes are large, like greater than 30. It's usually okay. The populations from which the samples are selected must have equal variances. That's an assumption called homogeneity of variance. Remember, in our independent measures t-test, we had to compute this using our F max. If you violate the assumption of homogeneity of variance, then it risks invalidating your test results. So you can't trust your test if you violated the homogeneity of variance assumption and the variance of your groups is too big, are too different from each other. Now, before we end our module here, I want you to work through one more practice exercise. In this situation, researchers want to compare happiness levels for those who are the richest third of Americans, the middle third, and the poorest third. Are there any significant differences between the classes? And where are they? Here are your data, the richest, the middle, and the poorest. These are happiness scores. I want you to perform the 4 steps of your hypothesis test using an alpha of 0.05. I recommend that as you do that, you put your results in an ANOVA table like this, with all 9 of these steps articulated. If your ANOVA is significant, then you should calculate a post hoc test as well, and calculate a measure of effect size, and then write it up as if for publication. Please pause your video, work through this example, and then when you're ready, move on to see the answers. Here are the answers to the ANOVA. You've got, in order to figure this out, you have to compute the mean of each condition, the sum of squares of each condition, the t of each condition, and also the n size of each condition, the number of conditions, the total n of your whole group, which I didn't write here, the g, the sum of x squared, and follow all 9 of those formulas in order to fill in your ANOVA summary table like this with your obtained f as 20.94. You should have found a critical f of 3.88. Your obtained f is much larger than your critical f, so you reject the null hypothesis and run some follow-up tests. Your post hoc tests use this Q. You put in these values. You get a HSD of 1.19, and you have to compare the means of the richest to the middle, the richest to the poorest, and the middle to the poorest. Those are your 3 differences, and you have to see which ones of these are larger than here. This and this are significant because they are larger than this critical value. This one is not larger than this critical value, so the groups here versus here and here versus here are significant. In other words, if you have a certain amount of money above being very poor, it doesn't matter if you are in the middle or the richest class of people, you are just as happy as each other. But if you're in the poorest class, you are less happy than the other classes. You would also compute your eta squared. You take the between sum of squares and the total sum of squares, and you pit them against each other, 4.77. You might interpret this as practice by saying 77% of the variability in happiness scores is accounted for by which class you're in. And then finally, you would write up a sentence as is for publication. It might say something like, the means and standard deviations are listed in table 1, and you'd put table 1, and you'd list the means and standard deviations, and then you'd say an ANOVA test indicated that there was at least one mean difference between the classes of people, comma, f, degrees of freedom, then your p-value less than 0.05, and then your eta squared, 0.77, and then you'd put a period and you'd say post hoc tests, probably specify the type. Tukey's HSD post hoc tests indicated that the richest Americans were happier than the poorest, and the middle Americans were happier than the poorest. But the richest and the middle were not different from each other. And that's how you do it.